Products fail a lot of the time basically because people fail to set objectives. They literally don't take the time to understand what they're building. And in an agile world, you hear it all the time. We've got to go fast, we've got to go fast, we've got to go fast, we've got to go fast. Go fast disease is okay, but go fast disease without any discipline is reckless and it's stupid. Sorry. If you look at the Agile Manifesto, it basically says, yeah, go fast, but you have to take the time to think about what you're doing and get it right. It's, yeah, you're going to build the least viable product, or you're going to do, but make sure that when you do it, you're doing it right. You're not doing it haphazardly or without thought, because that's the very first way that you're going to fail. Without goals, I go back to a book by Rob G., which is from the 1970s. He was with IBM. He was doing performance analysis. He was one of the very first people that were doing it. He is still a professor at Maryland University, I believe, okay? 80-some-odd years old. The first thing that he said in his book, the first reason why projects fail or why software fails is no goal. It is true today as it was in the 70s. If you don't have a goal, what have you done? I have no idea when I'm finished. Have I built the right thing? Is it going to work the way I want it to? Those are the questions that you have to ask when you're looking at why it fails. Attention to the user experience matters. Working for AGFA, what was it? Radiologists were working on systems that basically show radiological images, great big CT scans and so on and so forth. And guess what? If you took longer than 250 milliseconds to put the next image up on the screen, you had lost their attention. They were going like squirrels. Wow, cool. That's exactly what would happen to them. So if you didn't pay attention to that, if you didn't have that as a hard metric that you were looking for, they wouldn't like your system. And it was more or less subconscious. They wouldn't really even know why, but they just go, no, this system, I can't use it. Because their attention span would move off of it. We literally had to drive it down to 125 milliseconds. That's what we had to hit. But we had to have that as a hard target. And that's just lack of attention to basic user experience. Oh, I hate to say it, there's a lot of emotional baggage on this. Right? Adopting or adding performance fix-it-later syndrome. Oh, we'll build it, and then we'll make it fast. Big mistake, okay? That's one that just does not work. I always hear people go function, 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 then make it perform. Wrong. If you don't have it performing, it will never function the way you want it to. Yeah, it'll be a mock-up, and if you want a mock-up, that's okay. So, what is software performance engineering? Essentially, it's driving into the head of the project the thought process around getting performance established from the beginning. That's really what it does. And there's a way to do it. It's very easy. I love this. Everybody has a triangle, right? Measure, model, analysis. That's really what it's all about. And the nice thing about this, and I wish I had the animation that does this, but what you want to do is you want to make that triangle smaller. You want those to converge. You want those to get smaller. So you do measurement, you model it, you analyze it, you tweak it a little bit more, and you make that triangle smaller and smaller. Performance itself. I've got this quote from Mark, I think his last name is Rosenkowski, okay? And it was that performance is the currency of computing. Performance is what you pay for features, okay? And you're always paying a trade-off, one feature against another. Like if I do this, do I have enough to do the rest of my system? Well, if I take too much money over here, I don't have enough to get the user experience that I want. So I've got to give some money back, right? That's the currency of performance. You're always paying for it. And you're paying for it in CPU cycles, or I/O disk space, or network bandwidth, or whatever the measure is that you're using. Those are the things that you really want to determine whether or not you can do it at all. Is it really possible to do? So it used to be that we didn't understand how software functioned, okay? And a lot of research and a lot of time and effort went into making software function. We're there. It's easy. It's cookie cutter now, right? Unfortunately, along the way, we've lost some things like memory. It's just there to be used. Wrong. Okay. Memory is part of the currency of the system. Okay. But what you want to make sure now is that you are paying attention to it, that you're not letting it drift out of sight, and that you're, how can I put this? You want to make sure that your targets are reasonable and that they're adjustable. Performance is not something that happens once and you do it once. In fact, I've actually got something on that. Hey, oh yeah. Connie Smith and Lloyd Williams, they did the seminal work for software performance engineering in about 2000, thereabouts. That's when the primary research on this happened. Microsoft adopted software performance engineering, or SPE, during the phase where they were trying to fix Vista. Vista came out, it was a piece of, well, we won't go there, okay? But they used SPE to bridge that gap. They had such bad performance. They used it. And Smith and Williams, from that time period forward, the only thing really added to SPE since then is a measurement component that they didn't have in the original. Because in the original, they were primarily centered on guesstimation of what performance would be. Myths and legends. Again, one of these areas that there's a lot of, well, okay, I'll use the term again, emotional baggage. And especially that one. Performance is too expensive an effort. Oh my God. You know, I really want to kill. But at this point, people will say, yeah, we'll just get a performance test done at the end and they'll tell us what it is. I love this line. I have used it on a number of occasions. When it comes to the end of a project and somebody gives you something to performance test because you're the performance tester at the end of the project and you'll make it work. No. All I can do is hold up your software and go, the baby is ugly, and I can pass them back. Because at that point in time, it's too late. It does not work. It is an ugly baby. Yes, it's your baby, it's software, but it's, you know, back it goes. You guys must know the Seinfeld episode, right? Okay. That's where it comes from. It's a waste of time, don't over-optimize. I hear all these things from project managers and from software managers, okay, who are pressured for time, but they don't understand the power of SPE and what it can do for you. And this is one of the things that I want to try and overcome. Performance is hard work. That's part of the legend. Yeah, it is. But it's needed for success. This last point, okay, I always call the hope and pray methodology. We're going to build something, it's going to work, okay? And every once in a while it does. And that's the legend. One success a legend makes, okay? Because from then on, that person believes, oh my God, all we have to do is build it and it'll work. No. If you don't put the due diligence into it, if you don't look at what you're doing, it will not work properly. Just go for it. Oh yeah, I love this. There's a magic performance measure number somewhere. How many times have you heard somebody say, test this, I need it tested for performance? For what? Well, I don't know, just performance test it, tell me if it works. It works what? Well, it works better than the last version. Okay, now you've doubled my work. Okay, because now I have to go measure the previous version to figure out, well, how this one works, right? People don't really understand that performance numbers actually come from the beginning of a project where you define what it is. Hey, did I not click? Is it not doing what I want it to?
It's just being a bit slow.
Okay.
That's
Huh?
problem.
Oh, it's just new. Okay. So, foundations of SPE. Basically, the mathematics that are around SPE are threefold. Okay. Basic queuing theory. Okay. Theta notation. Okay. Here's a question I always ask. How many people took theory of algorithms? How many people, 20 minutes after the exam was over, forgot everything and have never used it since? One honest person. Yes. So, queuing theory on open and closed systems. What if in Monte Carlo analysis, that's kind of built into it too, it's part of queuing theory. Theta notation, algorithmic estimation of component complexity is really what it wants to do. And it's defined as an asymptotic bound. So what that means is as the software goes to infinity, as you build the load higher and higher, what does it approach? It approaches some function n. You can drop all the constants out of it, you can play around with it what you want to, it approaches some function of n. That n could be n squared, n cubed, n log n, whatever you want it to be, but it approaches that. Okay. Statistics, confidence intervals, frequency analysis, anything you want to think of, you can throw into statistics because everybody knows that the more statistics you do, the better it is, because 75.3% of the time, every statistic is made up on the spot. Okay? Queuing theory. Did anybody do queuing theory? Usually it is a master's level program. Sometimes it's an undergraduate. I've actually got Lily's husband is working on a course at U of W in ENCE for queuing theory.
Go.
Yay. So anyway, it really is the study of what makes a queue. Okay, and how can you get rid of the queues? Now, where do you find queues in computing systems?
Coders.
Hmm?
Routers.
Anything else?
Everywhere.
There are queues in everything. Anytime you do any communication between modules, between classes, between you and your database, between you and the outside world, everything can have queues in it. And you can design a queue system very simply. Little's law is the basic foundation of queuing theory. And really, all that states is if things arrive faster than I can service them, I'm going to get a queue. Okay? That's all it means. But the mathematical formulation of it is very elegant. It's really cool. And when you start digging down into it, there's all sorts of really interesting things that can happen. I've got a textbook probably about that thick on it. It's great. I suggest you read it. It's nighttime reading, don't worry. No, it's actually the way that this book is really written. It's very, very well done. I really enjoy it. So it helps you to define a better topology for a computing system so that you understand where things are. One of the things that queuing theory has taught computer science, okay, is to instrument. Okay. If you're not instrumenting your code, you can't find out where the queues are. And when it gets down to understanding, most people I tell them what you really want to have is, you know, everybody's got info and debug. Info tells you 3/4 of 4/5 of bugger all, okay? It just tells you that the machine is operating. And debug melts your disk, okay, because you're writing all this stuff off. You need an instrumentation layer in there, okay? That's lightweight and that can report when queues are filling, when queues are draining, how long it's taking to service things, and then when something doesn't perform. It's very easy to track and trace. I'm stepping ahead of myself. Theta notation. There's three big ones, okay? Big O, big theta, big omega, okay? That's what everybody knows about. But most people don't understand what the differences are between them. So if you look at big O is basically saying any function that I have, or whatever I'm measuring, I'm going to define a function that's going to be larger than that all the time. I'm either going to be at that or larger than that. If you're looking at omega, my algorithm is less than that. It'll take less time than this. Okay? So you can define it with one function. What most people don't understand is theta is bounding. Two functions that bound a function that is describing your system. Most people go, oh, theta is it, right? I've heard more people say big theta means that I found exactly what the algorithm is. No, you're finding that region that the algorithm will, or what the response time of the system will be in, not what it is, okay? And that's the primary difference between the three. The nice thing about it, and when you start playing around with theta notation, you can just discount all sorts of different things, and you can get rid of big constants and so on and so forth, because even though you've got, your algorithm is x cubed plus 3x squared minus 5x plus 17, I can take all of that off and I've got x cubed. Because as I approach infinity, it's going to be x as close as possible to x cubed. I don't have to worry about all that. I can simplify down very fast. I can do back of the envelope calculations very quickly. For an instance, these are just some log n and log n. If I started drawing n squared on that, it goes off the front right here, like really fast. But the interesting thing is, when I do a very quick back of the envelope calculation with this, I can swiftly tell you whether or not you're going to go to infinity fast. Okay? How many people know what an n squared algorithm is? It's a loop, right? A loop inside of a loop. What's a loop inside of a loop? N cubed. Okay, what's a loop inside of a loop? Inside of a recursion.
It's a recurrence relation.
Mm-hmm. Oh, it's a recurrence relation, but it's also exponential. Right?
Depends on your recursion.
Most recursions aren't that simple inside of loops. That's where usually people, like if you do a recursion inside of a loop, it's okay. But once you throw it inside of a loop, it can grow exponentially on you very quickly. It's one of those gotchas that you don't think of very often. And you go, oh yeah, I'll run this here. And it just so happens you're inside of a looping system and it goes nuts. I've had that happen. I've found that in at least 3 different types of software in 3 different companies. So it's a common mistake and it happens. Statistics. Statistics basically turns up the contrast. That's really what you're doing. You've got noise and signal, and they're not looking like anything, and you use statistics to kind of boost the gain, take a look at it, but there's danger with that, okay? The danger is looking at the wrong things, okay? The danger is looking in the wrong corner. The danger is a misinterpretation. All of those can kill you. Because you can go, yeah, this is what it does. Now, I've got a confidence interval of 90% that it does this, and people don't understand what a confidence interval is. Because a confidence interval doesn't mean it's this number plus or minus this. It means that the mean average will fall in that range 90% of the time. It's kind of like Nanos polls that you've heard recently, 2.3%, 19 times out of 20, which means they're saying 20%. Okay, if you look at the real numbers, that's what happens. Okay, same thing here, when you start to amplify noise, you get into a problem and an issue. So here are the SPE guiding principles. And these were the ones that were laid out essentially by Williams and Smith about 10, 15 years ago, okay? See, I got ahead of myself. Instrument. Okay, easy to see, easy to find. That's one of their primary principles. Instrument cues, instrument everything, be able to see what you're doing. But control of software performance comes from defining the metrics that you want to use. That's really the power of it, okay? Once you know what you're building, once you know where you're going, you can get more done, okay? You've got to make them feasible, specific, qualitative, and measurable. Nothing more. No big deal, but they've got to be realizable, okay? Nothing is worse than saying, I want it to work as fast as possible. It's not a metric that I can do, okay? If you tell me that you want something to operate at the speed of light, that's fine, except, guess what? In an electrical system, it doesn't operate at the speed of light. Light operates in a vacuum at the speed of light, okay? In copper, which is primarily what printed circuit boards are made out of, okay, it operates at 1/3 the speed of light. Because electrons, mobility inside of a solid is not the same as in a vacuum, right? So you can start to put down physical parameters that make these feasible and measurable. Independence, centering. Most software has an 80-20 rule in it. 20% of the software will be used 80% of the time. Performance, discount that that you don't need to look at, okay? There's 80% of your code that you don't even need to look at. It doesn't need performance. There's 20% of the code that does. Okay, that's the centering principle. Fixing point. What's the fastest way to get something done?
Don't do
No. Well, that's the procrastination style approach. Yes, okay. No, do it ahead of time, right? Get it done before you need it. So if you know that you're going, and this is a lot of predictive programming, is what that really looks towards, okay? Is saying, I'm gonna need this. I think I'm gonna calculate it first and have it, right? Such as you're working through potentially, let's say, a client's database, and you know that you're going to need name, telephone number, and so on and so forth, but you don't need it until you're printing it. Get it ahead of time. It's now sitting in cache, done. I don't have to worry about it, okay? Locality, reducing transfer time. It talks about designing in such a way that the modules that you have are working closer together, okay? Whether that's physical separation or logic, lost one, or logical separation, either way. Run once or batch, so frequency. You want to get around that. You want to know what's the best way to do it. You want to determine. Synergistic principles. Release more resources when they are not in use. Worst thing you can do, database locking, right? Oops. Database locking, getting rid of the resources that you don't need when you need them, so on and so forth. Parallel processing, threading efficiencies, and spreading the lower multi-node environments. Okay. Purely computational algorithm, okay? I give it to a single CPU on a single thread. If I give it 4 threads, will it complete faster?
Not usually.
Why?
Amdahl's law?
Hmm?
Amdahl's law?
True. Okay, it's purely computational. I've got a certain amount of cycles I've got to run to be able to do it. If I give it more threads, it's going to need the same amount of resources, it's going to take the same amount of time, in fact, it may take longer. Okay? Now, if I have 4 systems and I give them each a computational set of problems, a purely computational set of problems, and I give them 4 threads each, am I going to get it done faster?
Yes.
Maybe. Marginally, yes. You'll get a little bit faster speed out of it because there are efficiencies in doing that. You've got to understand that the more threads that you throw at something, you can actually slow it down. Okay? In integer-based software, which is what most people are working in now, okay? You're not doing floating point calculations, you're not doing atmospheric models where you're calculating differential equations at 5,682 points, right? Or, in three-dimensional space or whatever. You're doing operating system calls and so on and so forth, and they're all integer-based. There's efficiencies that can be done from threading there.
Coming in on secure channel.
Sorry. Okay, guilty, geek. Yeah, that's bad. Don't have to work that one. Okay, patterns and anti-patterns. So the other piece of SPE, you've probably heard of patterns, I hope. Have you?
People talk
Yes.
about them a lot. I've
Pardon?
heard people talk about them a lot.
Okay. Patterns are very, very well formed, okay? They're well known, and this is part of that bit I was talking about earlier about making function. Okay, we understand function. Okay, we know how to make things work now in software. It's not, well, it was rocket science. Now we're not doing as much rocket science. But they're well formed, they're very known. Anti-patterns, on the other hand, okay, there's a lot more anti-patterns than there are patterns. And a lot of the anti-patterns are very creative and very nasty, okay? They can really mess up a system very fast and do interesting things to it. So, basic patterns, example would be caching or prefetching, okay? It's going to one of the principles and basically saying prefetch stuff, have it ready when you want it, make sure that it's local. Don't go back to the database and get it again, okay? I just want to make sure that I've got everything that I need where I need it, okay? Minimize, optimize communication exchanges. But this is exceedingly important in the new microarchitectures, okay? Where you've got all these microservices all over the place. Way cool, very nice. However, one problem with it, one small perturbation in the API that causes one node to operate right and the next node to go wrong, okay? And that is a scientific term, it really does do that. It goes into oscillation or it goes into chaotic motion or whatever happens to it. It literally can destroy a system, okay? So you've got to make sure that your communication channels, you want to optimize them, you want to minimize them, and you want to control them. And that's basically, these are two very well-known patterns. Here's a few anti-patterns. Now they're more nefarious. The Alzheimer's program I love, okay? I'm going back and I'm getting the same data again and again and again. And I don't know how many times I've seen this. In fact, I have an example from yesterday. I hate to say this, and I'm being a little bit nasty, but I found a spot where I was calling the same select statement for one page 1,055 times. Okay? Why? There was one person looking at one piece of information, that was happening. So this happens more often than you know. The other one that's really nice, I like the empty semi-tractor trailer. It's one of my favorites. You change 4 fields, okay? So let's say that you change 4 fields. You have 256 characters in each field. You've got a K worth of data that you're changing, okay? You're sending it back to a database. And you send it back with 2.5 meg of framework behind it, okay? This is essentially the same as taking a chocolate bar, okay, in New York City, putting it into a semi-tractor trailer and sending it to California, okay? And then you want to send another chocolate bar, so what do? You do the same thing again. It is a waste of resources, it is a waste of time. It is things that happen. recursive looping is one of the other ones, actually. That's one of the anti-patterns that comes up. There are literally thousands of these that we have found. That's in the literature as well. So that's why anti-patterns is basically an entire semester's worth of work. I am not going to kid you and say that I can tell you all about anti-patterns here, because you can find them anywhere. You can find them in databases. You can find them. Oh, some anti-patterns actually work. Okay? How many people have used bubble sort? Okay? No. Why? Bubble sort's bad, right? Everybody tells you it's n squared, right? You know, it's bad. And I've got a really good story about that too, because it was a friend of mine who used to work for Citibank. And at lunch, they were having this discussion about, you know, about bubble sort and how bad it was. And this guy kind of went pale. And he disappeared and came back a little while later and he went, half of our MasterCards are being sorted with bubble sort for the whole bank. Right? Like, oh my God. However, if you've got something like you're searching something that's fixed data, such as 10 provinces, 50 states, using bubble sort is absolutely acceptable. Because it's quick, it's fast, it's dirty, it's easy. And it's not going to cost you a whole bunch of time, and the data's not going to change. It's not going to be 100 million that you're running through, you're going through 50. Or 62 if you can't count it. Right?
Except that you wrote a sorting algorithm, at which point something is definitely wrong with your code base.
Well, yeah, I'm just saying, like, if you have a small fixed data set, you can do it.
63, isn't it?
Hmm?
Then the 63?
Okay. Oh, yeah, because none of it's split. That's right. Yeah, okay. Okay, now I'm going to bore you with process. And I do mean bore you with process. This is the model that SPE has come up with. It's these basic steps, okay? It's put into a flowchart here. Everybody loves flowcharts, right? You know, but it's very simple. And one of the great things about software performance engineering, more than anything else, is this first decision tree. That first decision tree, I'm going to give this to Mary so she can distribute it around. Don't worry, don't try and read it here, okay? But that first decision tree says, is there any risk for performance in this project? If that answer is no, you're done. Okay? SPE costs you nada, because there is no risk. However, if I will say, document that risk before you actually move on. Okay, nothing is worse than walking up to a software programmer and going, did you think about performance? Oh yeah, we thought about it. Did you write it down? No. Okay, not a good answer to get, okay? Especially if their code is not performing at the end and they're wondering why. Once you've done that, that's basically identify your risk. You're actually going to identify what you want for objectives. Okay, that's basically construct the use cases that you want to construct the use cases, identify your objectives. This piece here, that's the model that you're building, okay? The model of the performance that you want to have. Since you've now got the objectives, you can actually go build a model, and you can look at the resources that you want to use, you can look at the things that you want to do with it, so on and so forth. This is not a tome. It's not a Bible. It's not huge. It may be PowerPoint positions, period. It's just a list. It tells you what you need to know and what you need to understand. Once you've done all that, you measure it, okay? And you keep updating the documents that you've got. So literally there's one document that you keep going. It's not a set of documents. This is not an overbearing process. Then you sit down and you go, okay, what quality do I have? Is the performance acceptable, yes or no? And I've actually got three choices. Yes, no, or there's no bloody way in the world we're ever going to get this to do it. Those are three acceptable answers, okay? If it's yes, I'm done. If it's no, and I can fix it, I go back up and I modify my scenarios, and I go back and I modify my model, and I keep on going. Because I can just churn through this. And I can turn the crank and I can get through this process. If it's infeasible, if I can't do it, if it's wrong, I just bail out and go, I set objectives that were absolutely unreasonable. Yes?
How do you know from the beginning that it will be unfeasible?
From the beginning, you don't.
Yeah.
And that's why you do this tuning all the way along. You're updating. You're not, it's never static. You never say, here's the performance, I'm done. No. Performance starts at the beginning and goes all the way to the end of the project. Okay? And it's due diligence. It's looking at it the right way. It's not being, how can I put this? I don't want to say reckless because it's not reckless. It's overly optimistic that you're going to, it's again the hope and pray. Okay, I'm going to get there just by thinking I will, right? I will build the performance again after I'm done. Again. So, as I said, this is not a long presentation. This is not a whole big thing. Performance is something that you need to change as a culture. Okay? Most people feel, I don't need to worry about performance. It's something that just happens at the end of a project. Okay? Again, my emotional baggage kicks in. I actually have to take drugs to deal with it. Okay? It really does get that bad at times. The cost of SPE. Traditionally, when you get to a business project and you say, we're going to build it, I get to the end, I don't have the performance I need, I've got to redesign it or re-architect it and go back to the beginning, I'm going to spend 200% of my budget now or more doing that. Because I have to go back to the beginning. Because the things that I have built into it make it intractable to hit the performance metrics that I want, so I have to go back and redesign. SPE on a very, very high-risk project has been calculated across a number of tracked projects. In fact, we did one internally, we tracked it, it was high risk, we found real performance issues, we fixed them. 9.7% of the budget was spent on SPE. Lines right up with the 10% that's here, okay? It works. It's not an overbearing process. This process alone, 10% of your time is spent in performance. And if you succeed at the end, you've only wasted 10% of your time and 10% of your budget. So you haven't wasted a lot of money. If you get to the end of the project and your customer goes, nope, sorry, it doesn't perform the way I want it to, boom, you're done. As well, in Agile, while you're going through this, okay, you can actually checkpoint with your customer as you do your demonstrations and go, is it acceptable? Yes or no? And if it's not, you can modify your performance at the time. You don't have to wait to the end when the customer goes, nope, sorry, not good enough. So that's part and parcel of why SPE is so important. Again, 0% if SPE is a low risk. If you don't have performance in a project, if your project is adding a widget to a page, okay, or a button, there's no performance there. Unless you're...
It's a button that starts bubble sort.
I can agree with you on that one. Proper SPE requirements, getting those goals done at the beginning of the project, actually give you a chance, a real good chance of knowing what needs to be built. Okay? Finding that little seed that, like I said, with radiologists, it's that 250 milliseconds that we have to hit. If we didn't know that up front going into that project, we would have been toasted by the end of it. Because we were doing CT scans, which were 2,000 pixels by 2,000 pixels. And what we ended up doing was doing compression algorithms that actually gave them low resolution first and high resolution over a period of about 20 milliseconds. It wasn't perceptible to the human eye, but it allowed us to do the algorithms better. Gives direction on how it needs to be designed, clearly defines the goals, can be used in both Agile and Waterfall. It's not one of these processes that it's only Agile, or it's only falling into Waterfall. It's not something that you have to, as I put it here, I think, no, sorry, that's how to measure, sorry. Slide beyond this, it's not bureaucratic, okay? It's very lightweight, it's very fast. How to measure performance? Again, we're back to the triangle, okay? For a very good reason, because in the projects that you're currently doing, do you know what you need to hit as a goal? And that's just a general question. Does everybody need to know, does everybody know what they need to hit in order to finish the project, in order to say it's successful? Really? Really? Okay. That's actually scary. Okay. If I was to say that I've got number of URLs per second that I can service, okay, as a metric, and I'm going to say that I need to hit 87,000 URLs per second to be able to do a specific project, to be able to hit a specific scaling point so that I can service this one customer. I can scale that down to one machine. And I know what I have to do on one machine, and then I know how many machines I'll need to be able to do the project. If I don't have those numbers, if I don't have that proper metric, if I don't know what my goal is, I don't know when I'm done. I could have been done 2 months ago, right? But I'm still working on the project because I'm getting that last little feature, okay? And that last little feature is your 95-5 rule, okay? There's an 80-20 rule for software. There's a 95-5 rule for projects, which is 95% of the project can be done in 5% of the time, and the last 5% of the project takes 95% of the time, okay? That last little inch is the one where people, they churn on it because they want to get that one more feature in it, okay? Are you already done? You don't know. You don't have a performance metric that tells you if you are or not. You're just getting another feature in. Sometimes that's called creeping features, by the way.
It's also an anti-pattern.
Hmm?
It's also an anti-pattern.
It's also an anti-pattern as well. Like I said, there's a lot of them, okay? Yeah, there's all sorts. The God class is one of the ones that everybody hears about. Okay, it's the perfect anti-pattern. There's one class that does everything, okay? And you keep going back to that class and it causes inefficiencies. That's the synergistic principle about distributing stuff out solves the God class problem. Like there's just literally, you can go on and say anti-patterns on the web and you'll get a ton of them coming at you. Readjusting the expectation. Remember I talked about minimizing that triangle? That's really what I want to try and do here. I want to pull that triangle down so that it's a dot. It all converges. That will never happen. That's when you're getting the 95, you're in that 95 percentile. You're in that last little 5%. But you want to know when you're getting close to that triangle being collapsed. It'll help you. This is exceedingly cultural, okay? And I say that because I tend to find developers that haven't been exposed to performance think in terms of a metric. I have to get this one thing. It's not one thing, it's a set of metrics. It's not just currency of performance is this one piece. It's all of it together. A system is a system. It's called a system for a reason, okay? There are different components that have to work together. And if you aren't looking at the entire system and you're looking at one thing, you'll bottleneck over here when we're looking at this. And then you'll never be able to get past this because you've got a bottleneck over here. It's a Venturi point. This one is also a little bit cultural. People tend to look for what they expect to see. That's why at the beginning, the software performance engineer keeps asking the questions. They are literally the obnoxious 2-year-old going, why, why, and about the 6th time that you ask why to somebody, you'll get the right answer. Okay? Because they'll finally break down and go, it's because we didn't have time. Thank you. You've beaten them down, but you've been the little 2-year-old. Okay. This is what SPE is not and is. Again, it is not that heavy, overbearing process that you have to track with a program manager, keep 14,000 copies of HIPAA documentation. You guys aren't dealing with HIPAA, are you? Good, because if you're dealing with HIPAA, then you're working with healthcare, and healthcare has this little checkbox which says may cause death. And as soon as you see that little checkbox, you're hosed. You've got to do documentation until the cows come home, okay? So it's really not a big process. It's very lightweight, and it was designed to be lightweight. The initial work that Connie and Lloyd did really was on estimating performance with blocks and adding numbers together. That's how they started out doing their research. It was going, how can I estimate this block? How many disk operations does it have? How many CPU operations does it have? And they took it that low, and then they slowly developed it out into Theta Notation and using that as tools to be able to do it. So the research started in a really cute place. So it is not unnecessary or costly. It's not a waste of time and effort. Performance is never a waste of time and effort. Again, you're talking to somebody who's, quotation marks, an advocate of, and potentially obnoxious. But that's because I have to pound on people all the time about performance, because it comes down to my office, we put it into the lab and we go, I don't like doing that. I do not want to tell you your baby is ugly. I want to get your baby out the door, because that it saves me time and effort if I can just go, done, gone. I don't want to do that. It integrates performance at the start of the project. It's a guideline to producing performant code, and it crystallizes what needs to be built. That really is the power behind SPE, is it literally can help you build something easily. And it's not that you have to understand all of queuing theory. You don't have to understand all of statistics. You don't have to understand theta notation, but you can take quick back of the envelope guesses at it. That's what's really powerful in this. And just keeping one little tiny document of your objectives and your record of what you've done, you're finished. It's not a huge thing. It's very simple. And trying to convince people or trying to break the culture of make it work, then make it perform, has been the hardest thing that I've had to deal with in the last 10 years. Because every time, we didn't have time to think about performance. We had to build it. We had to get the function set. Those are the words I hear. And those are words that kill me every time. Can you tell I'm passionate about this stuff? It's just one of those things where you see how much better it could be, and you just pound yourself into the floor, because they are under pressure. I must admit that developers are under pressure to get things done on a schedule. And as much as Agile has said that Agile is Agile, Agile still has a schedule. So it's Agile underneath Waterfall. There's very, very few places that I've found that have been doing pure Agile. And the ones that are doing pure Agile are doing performance. I found that. I was very, very surprised. There's a conference called CMG, Computer Measurement Group. This year, I think it's in, San Antonio, Texas this year. Okay, it's in November, late November. And you get performance people from all over the world going to it. I went to one in Reno, Nevada, okay? They put us out by the airport in a great big hotel with a great big casino, 2,000 people who knew statistics. Nobody played the tables, okay? There wasn't anybody in the casino. Why? They're all going, yeah, no, not me. They all knew, right? Same thing. The literally the energy that it's at the performance information that you can get from that. CMG is one of those places that you really want to go. So, as is normal, this is what most software performance engineers are. They're Sherlock. Okay, they are hunting under the covers. They are looking for the devils in the corners. They are looking for the lint. And how many people know what lint is? You do? You use Unix a lot. Yeah. So, any questions?
I have a question. So from a philosophical point of view, if the thought of thinking is make it work and then perform, statistically speaking, that's revealing a reality out there. You mentioned some of the causes of it, yeah? So then, is performance always a goal? You know what I mean? Maybe you have an application from your experience, yeah? Mm-hmm. Where you don't care about scalability, you don't care about,
yep.
If the reply is in a reasonable margin, yeah, then...
Right, and that's exactly what SPE does at the very beginning. Is there a risk for performance here, yes or no? If there's no risk, I'm gone. I'm out of there, I don't care about it. If I'm doing, and the one in particular that I'll tell you about was with, it was a research project done by somebody at the university, and it was on atmospheric modeling. And they spent tons of money. They had no concept of what performance was, nor did they want to, because their research was all about developing the algorithms around doing it, and what were the best methods to collapse sheets of differential equations into a predictive model quickly. So that they had absolutely no idea of what performance was. They just built whatever it was they wanted. Yeah, I've had projects like that, and you wouldn't do performance in that case, right? Now, I can't think of anything that's going out to a consumer that I don't think that there are performance metrics that need to be met. Okay, I can't think of anything that's going out the door that you're going to put in the customer's hand that you won't say, I need to have this. Otherwise, it's not going to be accepted, it's not going to be adopted. But yeah, there are times when performance isn't an issue, and that's okay.
This scenario that you described, that always people are saying make it work and then perform, yeah?
Yeah.
Maybe it's very hard to set at the beginning what the performance would be. You know what I mean?
Yes.
So
Agreed.
then how you get there?
Performance is not simple, okay, but it's iterative. You have to start somewhere. You have to have a target. And then as you go through, it's kind of like if you're doing an agile, let's say you're running agile sprints to get something done, okay? You have a target of, I need my user experience to be less than 1 second. Sprint 1, I'm going to say, this is prototyping, I'm going to put something together, 5 seconds is fine, I don't care. But by the time you get into sprint 3 or sprint 4, you're going to be tightening up the performance and saying, no, I need you to get below 2 seconds here, right? Because we need to hit 1 second at the end of the time period. So performance, as I said, it's iterative. It goes throughout the whole life cycle. It's not something that's done once here, and it's definitely not something that's done once at the end of a project.
Well, I think the biggest thing is that it's about the mindset the developer has as they're going through it. Because, I mean, like, the biggest anti-pattern you see on like a correct web app is N+1 queries, right?
Yeah.
And there's two ways that people handle N+1 queries. There's the popular way, which is to notice that your page is really slow and then check to see if there's any N+1 queries. And there's, right, which is make it work and then make it fast. And it's even there, that's not the end of the project, but it's still the mindset of, oh, I just wrote this page, and oh man, it's really slow. I wonder, maybe there's an N+1 query in there. That's usually what makes pages slow. And I'll come over to a coworker, and they're like, my page is really slow. Can you look at this? And I open up their source code, and I'm like, yeah, N+1 query, right here, right? But and so it's about the mindset of while you're coding to recognize what you're doing while you're doing it, and then you might still decide for whatever reason, oh, we'll tighten that up or whatever. But to know that it's there. And to recognize it, and usually by the time you recognize it, you know how to fix it. Usually, unless it's a really hairy one. And the biggest problem is to go through the whole process and not realize that you've even made the error until afterwards when you're testing.
I think
That's when you make a query to fetch a bunch of rows, and then you loop over all the rows, and for each row you make another query. Very popular, especially in any community that's using an ORM, because ORMs lend themselves to N+1 queries.
Yeah.
But I think the follow-on from that is that you'll only pick that up if n is reasonably large. So the danger is where the programmer doesn't even pick up that doesn't even go and look behind to see what's happening.
Right, which is an even bigger problem because they're usually testing on the 4 test users on their laptop, and then you push it out and you put the whole database in, and it's like, ooh, the page is suddenly very slow.
Yeah, and that's the thing is they're usually relying on some performance team further on to test it. And truthfully, there should be a performance team at the end. Don't get me wrong. That does
We call
put
them
it
the
underneath load.
users. We call them the users. Several million performance testers.
I've seen that pattern very, very often. Yes.
What's the difference between the test team and the performance team? I think the test team still be looking into the performance as well.
Yes.
Not just the why you specific a team that's only for the.
I didn't say that there was a performance team in this. The whole team is a performance team. Okay, so you've got the programmers and the people that are working alongside them, the test engineers. They're all working on performance from the beginning of the project to the end of the project. Yes, there should be a performance team down at the end that has, I will call it, excuse my language, a big-ass system that they can stress it against, okay? That you really want to do. You want to make sure that you don't have a breaking point in your software. But literally, testers, developers should be working in concert on performance throughout the life cycle of the project, right from beginning to end. Yes?
So I presume that the issue you face is that performance and scalability sometimes pull in the same direction, and in other cases pull in opposite directions, like the bubble sort versus other sorts. So I presume you have to be very clear in defining the two and making sure people know the difference between them.
Right. You bring up a point that I'm actually going to deviate a little bit first, okay? As I said before, people now know how to make software function, okay? And the quote that I heard talked about performance, but it also included in it scalability, manageability, serviceability, all of the abilities that are now part of a success of a product are becoming more important than the function. Because if you have the modularity, the serviceability, like all those things are now starting to become more and more important. And so, to your point, yeah, performance is just one dimension. There's multi-dimensions to this.
So it sounds like, I mean, you mentioned towards the end there, like it's not necessarily a big, expensive, complicated process, and it seems like that's true. But it seems like the real kind of meat of it is in the specification of performance. And it like so with your CAT scan example, you know, you knew that you needed the user to be or the process